Hello students, in this video we'll discuss the Cauchy distribution. A random variable x has a Cauchy distribution if its PDF, probability density function, is f of x, which is 1 over pi, 1 over 1 plus x squared for x between negative infinity and infinity. This is what a Cauchy distribution is. Okay? Let's first check to make sure this actually is a PDF. Clearly this function f is non-negative, so that's the first condition we need for PDF. The second condition we need is that it's going to integrate to 1. So let's check that. So if I look at the integral from negative infinity to infinity of 1 over pi dx over 1 plus x squared, I get a 1 over pi. An antiderivative of 1 over 1 plus x squared is tangent inverse of x, evaluated from negative infinity to infinity. I'm taking limits here when I'm doing this, but sort of we can note that I'm going to have a tangent inverse of what? A tangent inverse of positive infinity minus tangent inverse of negative infinity. And the tangent inverse of positive infinity is pi over 2, and this is negative pi over 2, so I get a total factor of 1 over pi, and then pi over 2 plus pi over 2. So we do indeed see that this is equal to 1, and we do have a valid PDF. Now we can use this same formula to find the cumulative distribution function of a Cauchy distribution. So let's do so. So the CDF is found by the following ways. F capital of x, and that's of course just the probability that x is less than or equal to little x, okay? And so this is going to be 1 over pi, and then the integral from negative infinity up to x of what? Of dt over 1 plus t squared. I have to introduce a dummy variable now, and so this is what? This is 1 over pi, and then tangent inverse of x minus tangent inverse of negative infinity, which is negative pi over 2, so plus a pi over 2, right? So what I have over here for the CDF is what? The CDF is going to be what? This is going to be a 1/2, and then plus tangent inverse plus 1 over pi, tangent inverse of x. Okay? Okay, so plus 1 over pi, tangent inverse of x. Okay? Now clearly as x goes to negative infinity, what's happening is going to negative pi over 2, so that's going to go to 0. When x goes to infinity, it's going to go to pi over 2, so I get to 1. So this is indeed a valid CDF. So that's what the CDF is, right? And so now, let's make a note about this. One note that happens is that the moments of these random variables do not exist, right? So the moments, just as a note, the expected value, for example, of x would be what? Would be this integral over here, 1 over pi, the integral from negative infinity to infinity of what? Of x over 1 plus x squared dx. And this function over here is not absolutely integrable, right? So this is not integrable function. This is not integrable. And so this expected value does not exist. And the same is true for any higher moments. So the expected values does not exist for this Cauchy distribution. And of course we can see this because as I take different limits, as I let one variable go to negative infinity and the other variable go to positive infinity, this term over here looks like a logarithm, and the logarithm does not converge as we go to infinity. We're going to have at different scales, this thing can give me different limits. So this limit does not exist because this function over here is not an L1 function, absolutely integrable function. So the moments of Cauchy random variables do not exist. So the first moment doesn't exist, the second moment doesn't exist for the same reason. All the higher moments don't exist for Cauchy random variables. But they do satisfy a beautiful property, and there's one beautiful property of these things, and that what I'd like to do is I'd like to consider if x is Cauchy, so let's say x is Cauchy, and if I look at a random variable, if I look at y, which is 1 over x, then I want to find the distribution of y is also Cauchy. Okay, let's prove that. So how do I prove that? Well, I'm going to consider the CDF for y. So let's let g of x be the CDF for y. So that's the probability that y is less than or equal to x. Well, if y is less than or equal to x, that says that's the exact same thing as saying that that's the exact same as the probability that that x itself is bigger than or equal to 1 over x by taking the reciprocal of both sides of the inequality, right? Okay, now I know what this is. This is 1 minus the probability that x is less than or equal to 1 over x. And now I can feed that into my equation over here. So this is going to be 1 minus 1/2 plus 1 over pi tangent inverse of 1 over x. Okay? So if we simplify this, what we have? We're going to have a 1/2 because 1 minus 1/2. And then we'll have a negative 1 over pi tangent inverse of 1 over x. So now if I do the derivative of this expression over here, the derivative of the CDF of y, that will tell me what the PDF of y is. So let's do the derivative of that. So if I take the derivative of this function, what will we get? So the derivative, so g of x is g prime of x. And that'll be what? It's going to be the derivative of this thing. The derivative of 1/2 is 0. Then I'm going to have a negative 1 over pi. The derivative of inverse tangent of anything is going to be 1 over 1 plus 1 over x squared. And then times the derivative of 1 over x, which is a negative 1 over x squared. And so, of course, these negatives are going to cancel out. And x squared times 1, so I'm going to have the negatives will cancel out of a 1 over pi. There's a 1 on top still. And the bottom of an x squared plus 1. X squared plus 1. Beautiful. That's the same as what? That's the same as this PDF over here. So in fact, 1 over x is also Cauchy. So the reciprocal of a Cauchy distribution is also a Cauchy distribution. That's beautiful. The Cauchy distribution comes up with all sorts of probabilistic applications, which you'll see more about in future videos. Thank you very much.